Thank you for your patience. Hi, everybody. My name is Yoav Tok from IBM Research. I'm a senior research staff member in IBM Research, and today I'll present to you the Fabric X order overview, which is a scalable ordering service for Fabric X. So let's start with the big picture of Fabric X. Fabric X is the new version of Fabric, and as you've heard last month, it's and you probably know from Fabric, it is composed of the execute order validate paradigm, where transactions are being pre-executed by either the peers or endorsers in a peer-to-peer fashion, sent to the ordering service, and then consumed by the committers and validated and committed. So today we'll talk about the ordering service. And I want to start by doing an overview of what the problem that we tackled was, what was the solution, what is the impact. So the problem is that Fabric performance today with Fabric version 3 with Smart BFT is around 2.5 K transactions per second. And this is not good enough for the future of decentralized finance, of asset trading, etc. So what we wanted to do is to improve on that. What we did to solve this problem is to re-architect the ordering service using three principles. The first principle is the separation of transaction dissemination from consensus. The second principle is introducing a lot of parallelism via pipelining and sharding. And the third principle is going with small transactions, basically stripping the certificates from the Fabric transactions. Doing so, we were able to reach performance of 150K transactions per second on a LAN and above 100K transactions per second on a WAN. This is 2 orders of magnitude better performance than Fabric. And all of this is in the open source in Fabric X order repo, together with the Fabric X project. So if you need to remember just one thing from this presentation, this is it. The problem is performance. We re-architected the ordering service, and we got to above 100K TX per second on both LAN and WAN. Now let's dive in a little deeper into the technical details. So I'll go back a step and describe what is an ordering service. Basically, it is a very simple thing. It's a service in which multiple transactions are submitted to by multiple clients, which we call endorsers, and they are submitted via the Fabric Broadcast API. The job of the ordering service is to produce total order of transactions, and it does so by bundling transactions into blocks and then total ordering the blocks. That's what we do. So the power is back. I hope you can see me okay. In Fabric, there is one process per ordering node, which can tolerate F failures. And we have in Fabric right now 2 flavors of this service. We have the CFT version, Crash Fault Tolerant, based on etcd Raft. And the minimal deployment tolerates 1 failure and needs 3 nodes. And the recommended deployment is 5 nodes and can tolerate two failures. This is depicted here in the picture to the right. The second flavor is BFT, Byzantine Fault Tolerance in Fabric v3. It's based on a library called Smart BFT. Again, the minimal deployment here is 4 nodes, and it tolerates 1 failure. Does the following thing. It takes a single ordering node, monolithic server, and breaks it to several components. It breaks it into a router, a batcher, a consenter, and an assembler. And this thing is called a party. A party here in Arma is a distributed implementation of an ordering service node. A party is an administrative unit, and in which components trust each other. If a component fails, we say that the party is faulty. And again, the router is symbolized by R, B are the batchers, C are the consenters, and A are the assemblers. So if we take the Arma architecture and we draw what happens when there are 4 parties, we see that each row in this picture is a party, and each column here represents the role. On the left, we see the endorsers, the clients of this service submitting transactions to the routers, 1 router per party. Batchers, we have as many batchers as we have the number of shards. And within each shard is a cluster communication protocol. And then we have each party contributing 1 consenter. And finally, each party has 1 assembler. Let me move on and dive into the main ideas that make the Arma protocol a performant one. So first of all, the main idea, the first idea here is to separate data dissemination from consensus. We disseminate blocks without consensus, and then we consent on block digests. Parallelism is implemented by introducing pipelining, breaking the processing to sequential stages and executing in parallel on different hardware. And sharding is basically horizontal scaling of functions that can be processed independently in parallel. And finally, small transaction, stripping the certificates from the access and keeping them in a registry or a cache. And I will not discuss small transactions today. This is a topic that is reserved to the Fabric X LFDT webinar next month. Now, let's zoom into the Arma architecture and take a look at the single party and try to identify these 3 principles in action. So first, data dissemination in parallel with consensus. What we see is that batchers send digests to the consenters, and the consenters are basically emitting total order on digests, not on batches, as in Fabric. So consensus is faster on smaller items, and a digest is about 10,000 times smaller than a block. That's one plus. The dissemination here in the green line is directly and in parallel from the batchers to the assemblers. The second principle is pipelining of validation, batching, consensus, and assembly. We see on the bottom here that the first stage does routing and validation, the second stage does the batching of transactions into blocks, and the third stage does consensus, and in parallel, the last stage, the assembly, is assembling a digest with blocks and emitting a total order of Hyperledger Fabric like blocks. The third principle is sharding. As I've said, and I will explain it a little more in a minute, the batchers are divided into shards, and these shards can operate in parallel. So this is an opportunity to do batching in parallel on different hardware. So these are the principles. And now let's go over a transaction flow in order to understand, by example, how does the Arma protocol work. So let's start with the endorsers on the left. These are the Hyperledger Fabric clients. They have a prepared transaction signed by the endorsers and signed by a client. What they have to do is a correct endorser is expected to send the transaction to all the parties, to all the routers, but must wait for two F+1 parties to respond in order to be sure that the transaction had been accepted. Once the transaction is in the routers spread the transactions consistently onto the different shards. So, for example, on this transaction number one, some deterministic function applied on the transaction decides that it goes to shard number one. And all the parties have to do the same. Each router sends the transaction to the batcher of its own party on shard number one. Once the transaction is in the shard, a protocol within the shard happens. The first stage of this protocol is implemented actually by the consensus cluster. The consensus cluster is the controller of each shard, and it determines who is the primary batcher in the shard, and it is marked here by a star. The primary batcher in the shard is in charge of creating batches, which later will turn into Hyperledger Fabric blocks. So it determines the batch and computes the digest on this batch, on this block. The next stage is to disseminate the block inside the shard to the secondary batchers. And the third stage is that every batcher that had persisted this batch send a batch attestation fragment, a short message to the consensus cluster. We call this a BAF, batch attestation fragment, and it basically contains the digest of this block. That's the main ingredient. And with some other identifiers that identify this block, in which shard it is, who is the primary, etc. And importantly, this BAF is signed by the sender. So a batch is a signed attestation that the batch exists at the respective batcher. And it is important to understand that the buff is small. This fragment is small. So now let's take a look at what happens at a consensus cluster. First of all, these four, in case we have four parties, these four consensus nodes form a BFT replicated state machine based on the smart BFT library, which is also used in Fabric v3. And the state machine does the following. It collects the batch attestation fragments and checks whether there are enough of them. Enough means F plus 1. So in the first time slot, we see that there's only one. It's not enough. Nothing happens. In the second time slot, we see that two other fragments had been submitted to the consensus. And since there are now four, which is more than F plus 1, in our example here, F is 1, F plus 1 means 2. So there are enough buffs to make a batch attestation. A batch attestation is a certificate that the batch exists in at least one correct batcher in the shard. Right? If there are F plus 1 attestations like that, fragments, then at least, and they are all the same, then at least one is correct. And then the state machine decides that this BA, this batch attestation, deserves to be included in the total order. That's what the consensus cluster does. The next stage in the transaction flow is to I mean, what I want to say here is that in each stage in the transaction flow, the consensus can order more than one batch attestation in the same decision. So in step number 2, there was only one. In step number 3, there are 2. Now, as I've said, the consensus cluster receives batch attestation fragments from the batches, which basically tell it, okay, I have a batch stored, and it includes these digest in decisions. The next stage is for the assembler to collate the batch attestations to full batches. What it does is it needs to fetch, according to each batch attestation, it needs to fetch batches from the respective shards. It replicates the decision and looks inside the decision to see which batches are already in the total order. So decision 1, as we saw earlier, there is nothing there, not enough fragments. Decision 2, there is a batch attestation that carries digest 1, which corresponds to the first batch, and it knows that it's in shard 1 somewhere. And then it can get it from shard 1 and put it in a block. In the next stage, the next stage, it will consume decision number 3. And here, instead of just one, there are 2 batch attestation, which means that digest 2 and digest 3 can be included in the ledger. So it will go to shard number 2, get the second batch, to shard number 3, get the third batch, and emit each batch in a Fabric block. Now, it's important to emphasize that the assembler, even though it looks simple, it takes the digest and then has to go to the batch and fetch it. For performance, it does prefetching of batches. So in practice, once the decision gets to the assembler already have the full batch in its prefetch buffer memory. And this is essential for performance. So to summarize the communication patterns that I had presented, let's go again from left to right, from the endorsers to the routers. and then we see the transaction getting to the routers. Transactions are flowing on the purple lines from the routers to the shards, to the batchers. Batchers do two different things. First of all, they replicate within in the green lines, and then they send full batches. The full batches are consumed from the batches directly to the assemblers. And batchers submit fragments or digests to the consensus cluster. And finally, the assembler is consuming a total order of digest on the one hand, and consuming the batches from the shards on the other hand, collating them, and producing a ledger full of Hyperledger Fabric-like blocks. Now, there is one thing. So this describes the data flow from the endorsers to the assemblers and then to the scalable committers, which consume blocks. They are essentially the peers, play the role of the peers. There is another ingredient here in red, which is the control loop. As I've said, consenters determine the primary of each shard here in yellow stars. But there is another role here which deals with detecting and handling faults. This is the next topic that I will describe. Faults here are subject to the following failure model. There are two kinds of faults. One is a crash fault, which is in which the server, when it fails, it just stops. And there are Byzantine faults in which a process or a server deviates arbitrarily from the protocol. This deviation can be malicious because someone had taken over the node, or it can be simply corruption, bugs, hardware failures, things that cause the server to behave erratically. So let me explain how this works with just a few examples. Failure one, first example, would be about a primary batcher crash. So a primary batcher will crash, and then this will be detected by the other three secondaries that want to replicate batches from it. Once they detect this crash, they will complain to the consensus cluster. The consensus cluster collects these complaints, and once there are enough complaints, it will change the primary, in this example, from party 1 to party 2. And the new primary will pick up where the old primary had left. This is one example of a crash failure. Now, there are other types of failures, Byzantine failures. I'll just give one example of transaction censorship. Say, for example, that the primary batcher is malicious. The primary right now is in party 1, and it wants to censor transaction number 4. All the other batchers, the secondaries, monitor transaction number 4 all the time. And if they detect that the primary batcher had not included transaction number 4 in a batch within a reasonable timeout, first timeout, they will assume that something benign had happened. Maybe a party 1 had not received this transaction from the client, etc., and they will simply forward it to the primary. However, once a second timeout had elapsed in which they did not receive this transaction, they will complain to the consensus, and consensus again will change the primary from party number 1 to party number 2. The third example of a failure has to do with the statement that I had mentioned before, that if a batch is included in a batch attestation, it means that there is at least one good copy of that batch in the shard, right? And it's in this example, this copy is in party 3 and party 4. Now, what happens to the assembler of party 1? It will always prefer to fetch these batches from the batcher of its own party. However, if it doesn't find it there, it has a mechanism to search all the batchers in the same shard and fetch it. So these are just 3 examples of how we deal with failures, both crash failures and Byzantine failures. And what I want to do is to summarize these different dimensions of failure detection and handling according to roles. So the consensus cluster is a BFT replicated state machine based on smart BFT. This is the same library that is being used in Fabric v3. So the consensus cluster is resilient to both crash failures and Byzantine failures. The batchers are controlled by consensus. So by virtue of complaining to the consensus state machine and consuming the decisions from the consensus state machines, which include the assignment of primaries and secondaries, etc. They are also, each shard is also Byzantine fault tolerant. The routers are simple components, they are stateless, except for the config. And the assemblers are also standalone components, which are pretty simple. They either, if they crash, they keep recovery state in their ledger. And if they are corrupt, they can be replaced and will replay the collation of batches to digest and reconstitute the state, or they will replicate from other assemblers. So handling failures of assemblers is fairly simple. The last dimension that we needed to take care of is communication. And we use the same mechanism as in Fabric, with using retries and BFT block pooling, like in Fabric. So I want to emphasize, again, using this architectural diagram, that the new ordering service is BFT, Byzantine Fault Tolerant, in which a party, here in the yellow box, is a single administrative unit in which components trust each other. Here, in our case, being BFT means that we can tolerate F-party failures. If here we have, in this example, we have 4 parties, we can tolerate 1 party failure. However, it's important to understand that for the correctness and the proofs, we consider a party as failed if some component within the party has failed. So if a component within a party fails, it is as if the entire party is faulty. So let's assume, for example, that party number 2 has a failure in one of the batches. We cannot tolerate, again, a failure in the consenter of party 4, for example. This violates the assumptions of F-party failures. This brings us to the issue of deployment. So as we know, in BFT services, the number of nodes is related to the number of failures that we can tolerate. In BFT, it's 3F plus 1. So if we want to tolerate 2 failures, we have to deploy n parties. Why f plus 2? This is because we can then bring one party down for maintenance while still having the tolerance for one more party. So it's an operational argument. In terms of deployment, we recommend that each party should reside in a single data center or availability zone or rack, something that fails together. And other parties should be deployed in different data centers or different availability zone or different racks, depending on the architecture of the deployment. One comment about storage and resource utilization. So if we look at the architecture of one party, and all parties are the same, what we see here are the communication patterns. Transactions flow into all the transactions flow into the router, and then transactions are being divided into the shards. So in this example, we have two shards. So half the transaction load goes into shard number 1, and the other half to shard number 2. This means that the storage in the batches accumulates, in this example, half of all the blocks. However, these batches are stored, but they are unordered. They are not yet included into the total order. The consenter, on the other hand, has a ledger, of course, of decisions, but this ledger is very small, and the traffic into the consenter is quite small. It's about 10,000 times smaller than the storage requirements on the batches. And finally, the assembler ledger contains all the blocks, all the transactions in an ordered fashion. So it consumes a lot of storage and has a lot of incoming bandwidth. We have a work plan to manage the storage accumulation in the FabricX orderer, which we will do in next year, of pruning some of the storage accumulation in the batches and implementing snapshotting, cold storage, and pruning in the assembler ledger. Now let's move on to some performance figures. We did several experiments, and what we see here is an experiment in which we use a typical transaction size of 300 bytes, and we load the cluster, the Arma network with as many transactions as we can, but while maintaining a latency below 1 second. And we plot the performance, the throughput, relative to the number of shards and the number of parties. So with the blue on the left-hand side, on a single data center, on a LAN, we see that we can, with 4 shards, we reach above 250K transactions per second. With 7 parties and 4 shards, we get to around 150,000 transactions per second. And we repeated the same, and we did also an experiment with 10 parties. We repeated the same experiment on a multi-data center environment using 3 data centers in the United States, in US South, East, and West. And we see that the performance degrades a little bit, but not a lot. Here we also here as well we see that we are well above 100K transactions per second for the recommended deployment size, which is 7 nodes. So we see that with 7 nodes and 4 shards, we are well above 100K transactions per second. So the main message here, we have a high performance ordering service in which for both LAN and WAN, we reach above 100K transactions per second. We also repeated the same, we did some experiments and in order to analyze the performance with failures. So we set up a typical deployment of 4 parties and 2 shards, and loaded it with 80K transactions per second continuously. And then at some point here in the graph at 60 seconds, we dropped a party. We shut down a party. And what we see is a temporary disruption on party failure, which corrects itself and goes back to the same level of sustained performance, 80K, after a while. However, what we see is that the response to failure depends on what were the roles within that party. If we drop party 1, which in this deployment contains the consenter leader in the smart BFT cluster, we see that performance drops to 0 for a few seconds, and then once a new leader is elected, performance resumes in the yellow line. If we drop either party 2 or party 3, they both have they have a leader, a primary batcher in shard number 1, or in the case of shard number 2, they have it has a primary batcher in shard number 2. When that happens, when a primary batcher fails, we see a 1/s drop in performance until a new primary is assigned. That's by the green and blue lines. And finally, if a follower or a secondary fails, then we see that there is no impact on performance at all. That's the pink line. So that is exactly what we expected, our resilience to failures. So finally, I want to conclude with the summary of the main message. We have a scalable BFT ordering service for Fabric X, which is largely compatible with Fabric APIs because we maintain the broadcast API in order to submit messages and the deliver API in order to consume messages. So the clients and peers, or the scalable committers, as we call it here, are largely consuming from the same APIs. We achieved performance by breaking down the monolithic Fabric order node into 4 server roles and applying the 3 principles. First, separating data dissemination from consensus. Secondly, introducing parallelism by introducing pipelining, executing in parallel, sequentially on different hardware, and sharding, executing in parallel horizontally at the same time on different servers. And finally, we are using small transactions, 300-byte transactions, which is something I did not describe in this talk. This will be covered in the next Fabric X LFDT meetup next month. So I urge you to join that talk as well. So the main message here is that we have 2 orders of magnitude better performance from around 2.5K to above 100K transactions per second. And our contributions are in open source. I encourage you to go to the Fabric X order repository and see the progress that we have there, the plan. We have a full plan, a lot of issues, several epics, and the plan to get to a release early next year. So that concludes my presentation. I'll stop sharing now and address some questions. Any questions?
Does amount of batches influence the performance?
The amount of batches? You mean the amount of sharding?
Amount
Yes.
of sharding.
Yes, absolutely. As I will share again. I will show you I'll share just this one. So as you can see here, you see my screen, this slide?
Yes.
Okay, so as you can see here, the routers split the volume of transactions into two shards. And within each shard, what happens is basically a broadcast function. So the primary batcher will broadcast the full transactions into all the other batches in the same shard. So this is a potential bottleneck. If we have only one shard, then the primary batcher will have to broadcast the entire volume of transactions. However, as the number of shards increase, then the burden on the primary batcher goes down according to the number of shards. So this actually realized that the potential to increase performance as the number of shards increase, as we see here. You see in both sides of the performance picture, both on LAN and on WAN, that performance increases with sharding.
Thanks.
Any additional questions? What are the minimal specs? Let me see questions in the chat. What are the minimal specs for each VM needed to run the orders? Okay, good question. So the numbers that I had shown here are from virtual machines deployed on the IBM cloud, nothing fancy. We used 32 VMs with 32 virtual CPUs. The RAM requirements are not large. A few gigabytes of RAM are enough. However, what we have here is dependence on the resource consumption varies between the roles. So the routers will need a CPU because they have to verify signatures, and they need bandwidth because they get all the transactions and they emit them to the batchers. The batchers are heavy on storage. That's the primary consumption. And here, I think storage is the big thing because with 100K transactions per second, 300 byte transactions, that's around 30 megabytes per second. Then transactions accumulates very fast in a high performance system. That's the most important thing in the batchers. The concentrators can be very light. They don't consume almost no CPU, very little bandwidth, and very little storage. The assemblers, on the other hand, receive all the transaction bandwidth, however, in the form of batches. So the incoming transaction networking pattern is very efficient, and they emit blocks to the peers. So again, the the networking patterns are efficient because large blocks are coming in, large blocks are coming out. However, again, the assemblers consume a lot of storage. So I would say that's the number one priority for VMs on the assembler sides. I hope that answers the question. Okay. Additional questions in audio or in the chat? So I encourage you to go to our repository, to the Fabric X, to Hyperledger Fabric X, to take a look at the documentation, to try some samples. We have Dockerized environment in which you can play. You can go ahead to Fabric X orderer and take a look at the documentation and the artifacts in which you can try this out. We'll be happy to get more questions on any communication channel you choose. We have a Discord channel for Fabric X. We'll be happy to get questions and to engage with the community. And our goal is to produce a release early next year, which will be high performance, production grade, and can take the Fabric umbrella ecosystem to the next phase.
Great. Well, thank you everyone for joining, and thank you, Yov, for that. And again, yeah, as he was saying, great to see you in the different community channels. If you have any other questions, comments, or interest in Fabric X, so thanks everyone for joining. And if anybody is interested in the next meetup that's coming up in about 7 minutes, we're having in this Zoom room a presentation on Web3J, so feel free to stay for that if you would be interested. So thanks everyone.
Thank you. Bye-bye.
Bye.